Hi there, welcome to this video where we continue taking a look at Richard Dedekind's essay, The Nature and Meaning of Numbers. This, all being well, will be the final video in this particular series. So we're taking a look at the final chapter of this essay, chapter 14, number of the elements of a finite system. Relatively speaking, this is one of the longer chapters of this particular essay. It's 10 or so pages long, so it's not long as such, but it's long in comparison to the other chapters. So there is the possibility that I might need to split the contents of this chapter into two videos, but I'm hoping to try to condense everything into a single video, even if it means that the video goes on for a little bit longer. Okay, so as usual, I'm going to be reading through the contents of the chapter, and I'm going to be giving my interpretations and of what Dedekind is saying, and elaborating on a few of the details. It will really help if you've got some familiarity with Dedekind's essay up to this point. So if you're jumping straight into this chapter, if you don't have any familiarity with this work, and you're jumping straight into this video, it's probably not such a good idea. You at least read the rest of Dedekind's work up to this point, otherwise you're not really going to know what I'm talking about in this video. Obviously, the other videos that I've made going through the contents of the rest of the contents of this work, feel free to watch them if they help you, but at the very least, make sure that you've read Dedekind's essay and then you're familiar with the ideas. Okay, so before we start, I'd be really grateful if you would consider subscribing to the channel if you haven't already done so, and hit the like button. Nothing that I say in this video is necessarily definitive, but if there is anything that's unclear, please feel free to ask any questions that you have in the comments section, or feel free to get in touch with me directly, whichever you prefer. Okay, so let's have a look then. So we're on with theorem 159. So if sigma is an infinite system, then is every one of the num systems Zn defined in definition 98 similarly transformable in sigma, i.e. similar to a part of sigma and conversely. So we've got a kind of if and only if sort of statement here. We've got on the one hand, sigma is an infinite system. So there's no requirement for it to be a simply infinite system. It's just an infinite system. Okay, and this is if and only if every one of the number systems Zn. So every Zn, remember Zn is kind of a finite, an initial finite part of the number series n. So Zn, the elements of Zn are all of the numbers of the number series up to, from 1 up to and including n. We can talk about these things now because we know what the number series is, we know how it's structured, and so on and so forth. So every Zn is similarly transformable in uppercase sigma. So one of these directions to prove is very straightforward. It takes 4 or 5 lines in here. The other direction requires a bit more work. We're going to have to go into a bit more detail. It's a bit more fiddly. So let's get going with it. Okay, so the proof. If sigma is infinite, then then by 72 there certainly exists a part T of sigma which is simply infinite. Okay, so Dedekind has already shown that every infinite system contains a simply infinite part. Now further down the line, this is maybe a little bit controversial, this kind of idea. Just to go off on a little bit of a tangent, for example, Cantor, in his 1895 essay, which I've done some videos on, he proves that every infinite aggregate has as a denumerable part or something like that. And effectively has to make essential use of what would become known as the axiom of choice. But Cantor understands infinite, he defines infinite in a different way, or he understands it in a different way to Dedekind. So Dedekind understands an infinite system or infinite aggregate, however you want to call it, in a particular way, namely that a system is infinite if it's similar to a proper part of itself. And because of the way that he defines it, it's much easier for him to prove that every infinite system has effectively what he calls here a simply infinite part, or a denumerable part. So similar to the number series n. The problem with the way that Dedekind understands infinite system as a system which is similar to a proper part of itself, to what extent this coincides with our intuitive understanding, whatever that looks like, of the distinction between finite and infinite, how well it captures that distinction is open to question. It does require the axiom of choice to kind of show that Dedekind's understanding of the distinction between finite and infinite does coincide with our more intuitive understanding of finite and infinite, which is based more on kind of one-to-one correspondences with numbers. I've discussed this in the video that I made for chapter 5, I think. So there's okay, just going off on a bit of a tangent there. Right, so therefore, by 132, similar to the number series n. So we've seen in 132 that every simply infinite system is similar to the to the number system n. Just let me double check. It is all simply infinite systems are similar to the number series n, and consequently by 33 also to one another. Consequently, by 35, every system Zn as part of uppercase n is similar to a part of T, therefore also to a part of sigma, which was to be proved. Because T is part of sigma. So any part of T is in turn part of sigma. By theorem 7, the transitivity of this relation, this part relation. Okay, so the proof of the converse, however obvious it may appear, is more complicated. So the hypothesis is that if every system Zn is similarly transformable in sigma, then to every number n corresponds such as... So that's the assumption that we're making. Every system, so it's in here, every system Zn is similarly transformable in sigma. In other words, there is a suitably corresponding similar transformation. Then to every number n corresponds such a similar transformation alpha n of Zn, that alpha n Zn is a part of sigma. So alpha n, this is there must be, if we're making the assumption that Zn is similarly transformable in sigma, there must be at least one similar transformation. So we can always choose an alpha n. So alpha n is one of these similar transformations that takes elements of Zn and similarly transforms them into sigma. So we naturally get that alpha n Zn is a part of sigma. From the existence of such a series of transformations, alpha n, regarded as given, but respecting which nothing further is assumed, so we don't assume anything other than they are similar transformations, and there is at least one of them, We derive first by the aid of theorem 126 the existence of a new series of such transformations psi n, possessing the special property that whenever m is less than or equal to n, hence by 100, Zm is a part of Zn, the transformation psi sub m of the part Zm is contained in the transformation psi n of Zn, i.e. the transformations psi m and psi n completely coincide with each other for all numbers contained in Zm, hence always psi m of m is equal to psi n of m. So that's in the case where m is not greater than n, or is at most as great as n, or however you want to phrase it. Okay, so in order to apply the theory, so what's going to happen here is Dedekind is going to, we're going to have on the one hand n, and on the other hand, sorry, we're going to have we're going to have Zn's. So we're going to have n, and we're going to be considering parts of n. We're not going to be here considering n as a whole. We're just going to be considering parts of n, these Zn's. And he's going to form another system, omega. And he's also going to form a transformation, theta, which is a transformation of omega in itself. And what we're going to be able to do then is to apply the result of theorem 126 to get the transformation that we need. So there's quite a bit of work involved in this. It's a little bit fiddly, so I'm going to take my time with it. As usual, bear in mind that this video is unscripted, so I might just have to think a little bit. I have read through this a couple of times, but you know, sometimes I might still need to just think a little bit about what I want to say, how I'm going to express what I want to say. Okay, so in order to apply the theorem stated to gain this end, we understand by omega, that system whose elements are all possible similar transformations of all systems Zn in sigma. Okay, so this is what we understand by omega. It's this system of similar transformations. So all of the transformations from Zn in omega for each n. Okay, so it's not limited. Omega is not in sigma. God, I'm getting mixed up with my sigmas and omegas here. So it's not, omega is not all of the transformations of Zn for some fixed n in sigma. It's all of the similar transformations of Zn for each n. Okay, and this is going to be quite important because that's this theta, the transformation theta that is going to be constructed is going to rely on that fact. And by the aid of the given elements alpha n likewise contained in omega, we define in the following manner a transformation theta of omega in itself. So what he does then is he takes a beta. So beta is any element of omega. So in other words, beta is a similar transformation. Transformation. And in particular, it's a similar transformation of some Zn into sigma. Okay, so for beta is a fixed, we're choosing it, so it's a fixed transformation for all intents and purposes. So it corresponds to some fixed Zn. So presumably we've got some way of recognizing, given a particular transformation from omega, which Zn it corresponds to. Presumably we've got some way of recognizing that. Thus, example, a similar transformation. So if beta is any element of omega, thus example, a similar transformation of the determinate system Zn in sigma, then the system alpha n primed z n prime. So these what's happened here is for each zn has been chosen effectively an alpha, a transformation alpha n which corresponds to it. Okay. Now this is potentially quite controversial as well, this particular step, because no rule has been given how these are to be selected, how this sequence of transformations is to be selected. So there's some more details about this in Moore's. If you read Moore's book, Zermelo's Axiom of Choice, on page 26, there's a bit more information regarding this. But this alpha n primed here, it's referring to this sequence of transformations that Dedekind has chosen. So he's chosen an alpha 1, an alpha 1 primed, alpha n primed, and so on and so forth. How these are chosen is arbitrary, and that's part of the controversial bit. So that's this transformation here that he's talking about, this alpha n primed. So this has been chosen beforehand, effectively. So alpha n primed cannot be part of beta zn, for otherwise zn primed would be similar by 35 to a part of zn, and hence by 107 to a proper part of itself, and consequently infinite, which would contradict theorem 119. So what's he talking about there? So if we've got the numbers 1, 1 primed, n primed, then a little bit too short. So this is the system Zn, and then this is the system Zn primed. Okay, so we're going to use beta to transform Zn. So remember, beta it's an arbitrarily chosen similar transformation from omega, but it must correspond to some particular Zn. So we're going to transform each of these elements, and we get beta 1, beta 1 primed, beta n, and everything in between. So what Dedekind is saying here, and this is going to rely on the similarity of beta. So, okay, it might be worth saying that if beta is a similar transformation, then the inverse of beta exists, and it too is a similar transformation. Okay, so beta bar, which goes in the other direction, is also a similar transformation. So if alpha n primed of Zn primed were actually a part of beta Zn, then that means that all of these 1 primed, n primed would all be amongst these values here. So beta 1 primed, beta n, they would all be in there somewhere. So what we could do then is form the transformation alpha n primed beta inverse, and this would not by definition necessarily, but this would be a similar transformation because alpha n primed is a similar transformation, beta bar is a similar transformation, so the compound of the two is also a similar transformation. So we can transform all of the elements 1 primed, n primed, but by using transformation alpha n primed, and then transform them back into numbers. So we're taking them into the system sigma, and then we're taking them back into the number system. But because evidently all of the transforms of 1, 1 primed, n primed are amongst the beta 1, beta 1 primed, beta n, then when they're transformed back, they'll be transformed back into some element of Zn, not into Zn prime. So none of these will be transformed into n prime. So therefore, Zn primed would be similar to a proper part of itself, which is not possible. Because Zn and Zn primed are both finite. In particular, Zn primed is finite, so any part of it is going to be finite. So that would be a contradiction. So in other words, we cannot have this. Okay, so he seems to make a big deal about it, but it's important to be thorough with all this kind of stuff and not take it for granted. Okay, so alpha n primed Zn primed is not a part of beta Zn. So if it's not a part of beta Zn, then there must be some elements of this which are not in of alpha n prime Zn prime, which are not in beta Zn. Okay, so therefore there certainly exists in Zn primed one number or several numbers p such that alpha n primed p is not contained in beta Zn. Okay, so this alpha n primed has been arbitrarily chosen. It's got no particular relationship to beta. So again, we've got the numbers 1 primed, n primed. Beta will transform each of these into beta 1 primed, beta n. In fact, beta won't touch n primed. And then on the other hand, we've got alpha n primed, which will transform each of these. I'm not drawing this very well, am I? Into alpha n primed 1, alpha n primed 1 primed, alpha n primed n prime. Now, some of these alpha, it might be that, I don't know, alpha n primed 1 primed has the same value as beta n. Possibly. Okay. By the way, these similar transformations, they don't need to preserve the order, any kind of order necessarily. In fact, we don't necessarily have an order on Sigma anyway. All we know about Sigma is that it's just a system. We don't even know that it's infinite. At this stage, that's what we're trying to prove. So some of these alpha n primes are going to coincide with some of the betas in general, but also there are going to be some of the alpha n primes, maybe this one, which doesn't coincide with any of the betas. Okay, so there's going to be some numbers in amongst these numbers 1 to n primed. Some of the transforms alpha n primed of that number will coincide with some beta, but it doesn't necessarily have to be the same number. So it doesn't have to be that alpha n primed of 5 is equal to beta 5. It doesn't have to be that. It could be that alpha n primed of 12 is equal to beta 5, for example. So it's just that some of the alpha n primes will coincide with some of the betas, but we don't necessarily know which ones. But there will be some numbers, and there must be at least one number, because the transformation beta is a similar transformation of Zn into sigma. Alpha n primed is a transformation of Zn primed into sigma. So as we might expect, and this will kind of be proved later, Zn primed has that extra element in there, n primed. So absolute worst case scenario, and mathematicians always take this into consideration, absolute worst case scenario is that alpha n primed coincides with beta on all of the values 1 to n. And then it's just n primed that's different. Now, that's a very extreme case, but that has to be taken into consideration, and this is why, in my opinion, Dedekind has specifically chosen alpha n primed. So he's got the transformation beta, which is a transformation of Zn. He specifically chooses alpha n primed, which is a transformation of Zn primed, so that he's got that extra element to play with. So, taking into consideration this worst case scenario. But in general, there's going to be a whole bunch of numbers in here between and including 1 and n primed, such that alpha n primed of p does not appear amongst the betas. So what he does is he takes the least p, okay, the least number p, which we can always do, because we've proved, or Dedekind's proved, should I say, that every part of the number series n has a least value. In other words, it's we'd say now that that's it's a well-ordered set or something like that, right? So because of this well-ordering, which has been proved, just not in those using those words, then we can always choose this least element. So let's see what where this leads us to. Therefore, there certainly exists in Zn primed one number or several numbers p, such that an primed p is not contained in beta Zn. From these numbers p, we select simply to lay down something determinate, always the least k. So, so amongst these numbers p, we take the least and we call it k. So therefore, alpha, in particular alpha n primed k, is not equal to any of the betas. That's the key point here. That really make sure that you've understood that, because that is going to play a role. That the way that this element is chosen is going to play a role further down the line. So if it does seem that I'm kind of labouring the point a bit, that's because I am. And since Zn primed by 180 is compounded out of Zn and n primed, define a transformation gamma. Right, so I'm going to clear some space here. So define a transformation gamma of Zn primed, such that for all numbers m contained in Zn, gamma m is equal to beta m so that's for all effectively for all m as part of Zn. And then gamma n primed, or m is less than or equal to n if you prefer, gamma n primed is equal to alpha n primed k. This obviously similar transformation gamma, and it must be similar because remember alpha n primed k was specifically chosen because it didn't coincide with any of the betas. So because beta is a similar transformation, then because alpha n primed k doesn't coincide with any of the betas, then gamma of n primed is different to, so gamma n primed is different to gamma m whenever m is less than or equal to n. Okay, so that satisfies the conditions for similarity. So gamma is a similar transformation of Zn primed in sigma, We consider then as a transform theta beta of the transformation beta, and thus a transformation theta of the system omega in itself is completely defined. So remember, omega was a system of transformations, similar transformations. So this theta of beta, is effectively this transformation gamma. It's constructed in this way just described. So what theta does is it takes a transformation from omega and it extends it. It extends the transformation. So it looks at beta, says, okay, this is a transformation. So remember also we've got all of these selected: alpha 1, alpha 2, alpha 3, alpha n primes, and so forth. We've already selected all of these. So we choose our beta. We look, okay, this is a transformation from Zn into sigma. Okay, so now I'm going to use this transformation or this alpha n primed, and I'm going to take one of the values of that doesn't appear amongst these betas, and I'm going to plonk it on the end. And in this way, I extend beta into a new transformation, such that this new transformation is identical with beta when it's restricted to the values of m less than or equal to n, but then it's got this new value stuck on the end. So theta is like an extension. It extends the transformation beta. It's quite clever how it works. And it's this theta that is going to correspond to the transformation in theorem 126. After the things named omega and theta in 126 are determined, we select finally for the element of omega, denoted by lowercase omega, the given transformation alpha 1. Remember, these have already been chosen. Alpha 1, alpha 2, so on and so forth. It's just now we use this alpha 1 specifically as our base element. So notice that this choice, how this theta extends beta, will depend on our choice, or our initial choice of function, of transformations, alpha 1, alpha 2, alpha 3, and so on and so forth. So if I choose alpha 1 primed, alpha n primed, I will get a particular way of, this will determine a particular way of extending transformations in omega. If you, on the other hand, choose alpha 1 primed, in general, you're going to choose differently to me. And therefore, the way that you extend transformations in omega is, in general, going to be different to how I do it. The technique is the same, but the specific transformations that we end up with, the specific way that we kind of wind our way through omega using this transformation theta is going to be different. But that doesn't make any difference. That doesn't really affect things. So thus by 126 there is determined a transformation psi of the number series n in omega, which if we denote the transform belonging to an arbitrary number n, not by psi n, but by psi sub n, satisfies the conditions 2 and 3. Okay, so let's just take stock of where we are then. So on the one hand we've got n, on the other hand we've got omega. We've got 1 primed, n primed, and so on. Over on the omega side we've got alpha 1. That's our base element. That is effectively our omega, lowercase omega. And then we apply theta to get theta alpha 1. Okay. So we, our function, I keep using the word function, transformation, psi. So we are using theorem 126, and it is a transformation on each number that applies to each number in the number series, and in other words, the number series as a whole. So this is equal to psi 1, but because it is a transformation, Dedekind decides to use the notation psi sub 1, which to me makes more sense because it kind of emphasizes that it is still a transformation. Psi 1 in brackets, that suggests that it's going to be some fixed value, not necessarily a number, but it's going to be, it doesn't emphasize that it's a transformation. Psi sub 1 emphasizes that it's a transformation. So then we apply theta, and we define this to be equal to psi of 2. Apply theta again, and we get what is going to be psi 3, and so on and so forth. Okay, remember 1 primed is 2. So it's working exactly in the way that theorem 126 kind of suggests it should work. So by complete induction, 80, it results that first that psi n is a similar transformation of Zn in sigma. So again, I need to clear some space, don't I? So we're doing an induction to show that psi is a similar transformation, which theorem 126 itself doesn't guarantee. All theorem 126 guarantees is the existence of such a transformation psi. It doesn't guarantee that psi will be a similar transformation. So we've got a bit extra work to do here to prove that psi is actually a similar transformation. So by 2, this is true for, so in the case when n equals 1, we know that psi 1 is equal to alpha 1, and therefore, because alpha 1 is, I mean, it's trivially a similar transformation. Any transformation which is a transformation of a single element system is always going to be a similar transformation. And sigma, this is the second part of the induction. If this statement is true, so in other words, psi n is a similar transformation, it follows from 3, so namely that psi n primed is equal to theta of psi n, and from the character of the above described transition theta from beta to gamma, that the statement is also true for the following number n primed, which was to be proved. So psi n is a similar transformation. Theta, by its very construction, by the way that it's defined, is a similar transformation. So I'm not going to go into the details, but it's kind of obvious, really, that theta is going to be a similar transformation. If you take a beta 1 and a beta 2, for example, which are not equal, then you apply theta to each of these, then you will end up with theta beta 1. So if these are unequal, theta beta 1 will not be equal to theta beta 2. So theta is a similar transformation also. So therefore psi n primed is a similar transformation because it's a compound of 2 similar transformations. Okay, on to the next page. So afterward we show likewise by complete induction that if m is any number, the above stated property, so psi n m is equal to psi m for m less than or equal to n or n greater than or equal to m actually belongs to all numbers n which are greater than or equal to m, and therefore by 93 and 74 belong to the chain of m. So in fact, rho, again, an induction in the case when n is equal to m in this case, so the base case is not n equals 1, it's n equals m. Well, I mean, that's kind of obvious because then we get psi m of m from here is equal to psi m of m. Well, yeah, that's kind of obvious, really. Okay, so if this property belongs to an... So if we're able to show that psi... so we assume that this holds... in fact, no. I was going to say something. I've changed my mind. So if we assume then, if the inductive hypothesis here is that this holds, psi n m is equal to psi m m for m less than or equal to n, we need to go on then to show that it also holds for psi n primed of m is equal to psi m of m. It follows again from 3 and the nature of theta that it also belongs to the number n primed, which was to be proved. Okay, so psi n primed of m is of course equal to theta psi n of m. That's by 3 on the previous page. Using the inductive hypothesis, this is theta psi m of m, which, so that's it. That's my hypothesis, which in turn is equal to psi m primed of m. So this is important. This is where I was saying earlier that it's important to pay attention to how this transformation theta is constructed. As we move from, so I'll use m and m primed instead of n and n primed. So we start with a transformation of Zm, and we apply theta. We use this construction to get a transformation on Zm primed. But this new transformation that we obtain, this theta, so maybe I should have used beta here. The transformation beta, we end up with theta of beta. Theta of beta coincides with beta on all values. It's a transformation of Zm primed, but it coincides with beta on all of the values up to and including m. So it leaves all of those untouched, right? So in other words, psi of m primed of m is also equal to psi m of m, right? Because we've applied the theta here to psi m of m, but it leaves all of the values untouched up to and including m. It just extends from a transformation of Zm into sigma to Zm primed into sigma. So therefore, we've got that psi n primed m is equal to psi m of m, which is what we needed to show. So if psi n m equals psi m m holds for some n, then it also holds for n primed, which is what we needed to show. That's the property that was stated on page 106. Okay, so after this special property of our new series of transformations psi n has been established, we can easily prove our theorem. We define a transformation chi, getting mixed up with my Greek letters, chi of the number series n, in which to every number n we let the transform chi n equal psi n of n correspond. Obviously, by 21, all transformations psi n are contained in this one transformation chi. Since psi n was a transformation of Zn in sigma, it follows first that the number series n is likewise transformed by chi in sigma. So in other words, we've got chi of 1 is equal to psi 1 of 1, chi 1 primed is equal to psi 1 primed, 1 primed. Generally, we'll have chi of m is equal to psi m of m. Okay, but this psi, by what we've just proved, psi 1 primed of 1 will be equal to psi 1 of 1. And similarly, we'll have that, for example, psi m of 1 will be equal to psi 1 primed of 1, which is equal to psi 1 of 1. So all of these, it's like a nested series of transformations, if I can word it like that. Okay, each of these transformations, psi 1 going to psi 1 primed, leaves, when we restrict to just so if we look at psi 1 primed, I'm kind of repeating myself here. If we consider m just equal to 1, then it coincides with psi 1. The only new value is m equals 1 primed, or 2. For psi of 3, this will coincide with psi 2 for the values 1 and 2, and coincide with psi 1 for the value 1. So the only new value of psi 3 is 3, right? Psi sub 3. The only new value is psi sub 3 of 3. So we've got this nested sequence of transformations, but this is nothing new. We've done this before. We saw this in theorem 126. It's completely familiar to us. So also, because each of these psi 1 of 1, psi 1 primed, 1 primed, psi m of m are all parts of sigma, then all of the system of all of these values together is also part of sigma. So in other words, chi of n is a part of sigma. So if you want to think about this as a system compounded of all of these values, you can do. When Dedekind defined a system compounded out of other systems, he didn't limit it to a finite number of systems. So you can think about it that way if you want to. If further m and n are different numbers, we may, by reason of symmetry, according to 90, suppose that m is less than n, so without loss of generality and all that business. Then by the foregoing, chi of m is equal to psi m of m equals psi n of m. Okay, so so chi of m is equal to psi m of m, which is equal to psi n of m, and that is for all m less than n. And then we've got chi n is equal to psi n of n. So what he's doing here is for all values up to and include, so choosing some fixed n, we can show that chi for all values up to and including that value coincides with psi n on all those values. Okay, so if we've just got 1 primed up to n, then chi on all of these values coincides with psi n. but since psi, and the reason for this is because then chi is going to be a similar transformation on this system of numbers, on effectively on Zn. Because psi n was a similar transformation, then chi must also be a similar transformation of Zn into sigma. But since psi n was a similar transformation of Zn in sigma, and m and n are different elements of Zn, then is psi n m different from psi n n, hence also chi m, which is equal to psi n m, different from chi n, which is equal to psi n n, i.e. chi is a similar transformation of n, of uppercase n. Since further uppercase n is an infinite system, by definition 71, the same thing is true by 67 of the system chi n, similar to it, and by 68, because chi n is a part of sigma, also of sigma, which was to be proved. So the same thing is true by 67. So what's 67? If R and S are similar systems, then is R finite? Right, okay, so n is an infinite system, therefore chi of n is an infinite system. And because chi n is part of sigma, then that means that sigma also is an infinite system, because by theorem 68, every system S which possesses an infinite part is likewise infinite. So sigma possesses an infinite part, namely chi n, therefore sigma is an infinite system, which was to be proved. So we're done. Oh, we're on to the next page, actually. So that was quite a long theorem. That's probably one of the most challenging proofs to go through in this work. Having said that, it's not, in principle, it's very simple. The idea, it's just following the details. It's easy to get lost in the details, but once you've found your way through it, then it's really not too bad. Okay, so theorem 160. A system sigma is finite or infinite according as there does or does not exist a system Zn similar to it. So if sigma is finite, then by 159 there exist systems Zn which are not similarly transformable in sigma. Okay, so remember what 159 said. If everyone, sigma is an infinite system if and only if every one of the number systems Zn defined in 98 is similarly transformable in sigma. So if there is no such number system Zn which is similarly transformable in sigma, then sigma is a finite system. Or vice versa, if sigma is finite, then there's no such Zn which is similarly transformable in sigma. Since by 102 the system Z1 consists of a single number 1 and hence is similarly transformable in every system. That's what I was saying earlier, that every system that consists of a single element is similarly transformable. It's trivial, right? It's obvious. Then must the least number k to which a system zk not similarly transformable in sigma correspond to it corresponds in sigma corresponds be different from 1, and hence by 78 equal to n prime. So the only every number in the number series that is not equal to 1 is of the form n primed, where n is a number in the number series. So in other words, every number in the number series except for 1 is the transform under phi is the transform of some number. Okay, so 1 can be transformed into another number using phi, but no number transforms into 1. And that's one of the characteristic features of the system N. So there is a ZK which is not similarly transformable into in sigma, and K is equal to N primed for some suitable N. And since N is less than N primed, so that's by 91, there exists a similar transformation psi, so Zn is similarly transformable into sigma, and we can use the transformation psi if then psi Zn were only a proper part of sigma. So assume that psi Zn is a proper part of sigma. Then since Zn primed, so this is by theorem 108, is the system compounded of Zn and N primed, we could extend this transformation psi to a similar transformation psi of Zn primed in sigma by putting psi N primed equal to alpha. So what's alpha? Where did we get alpha from? Oh, sorry, yeah. So if there existed an element alpha in sigma not contained in... So alpha is not... It's not a part of psi Zn. So we can set... we can extend the transformation psi to a similar transformation of Zn primed by setting psi of N primed equal to alpha. While by our hypothesis, Zn primed is not similarly transformable in sigma. Hence, psi Zn equals sigma. Okay, so we've got a contradiction. By assuming that Zk is not similarly transformable into sigma, where k is equal to N primed, we've actually arrived at the conclusion that Zn primed is similarly transformable into sigma. So we've got a contradiction there. So therefore, Zn is... psi Zn... So this alpha doesn't exist, effectively. There is no such alpha, and therefore psi Zn must actually be equal to sigma. I.e. Zn and sigma are similar systems because psi was a similar transformation. Conversely, if a system sigma is similar to a system Zn, then by 119 and 67, sigma is finite, which was to be proved. Because Zn is finite, and by 67, anything similar to a finite system must itself be finite, right? Yeah, so if R and S are similar systems, then is R finite or infinite according as S is finite or infinite. Okay. Definition 161. If sigma is a finite system, then by 160... that's what we've just proved, yeah. Then there exists one, and by 120 and 33, only one single number n, to which a... So let me check this out. Only one single number n to which a system Zn similar to the system sigma corresponds. So 120 is, if m and n are different numbers, then Zm and Zn are dissimilar systems. If sigma is similar to Zn, it cannot also be similar to Zm if n and m are different numbers. What's 33? R and S are so if sigma is similar to Zn, and it's also similar to Zm, then Zm and Zn must be equal, or they must be similar at the very least. And they can only be similar in the case when n is actually equal to m. So yeah, okay, it all adds up. This number n is called the number of the elements contained in sigma, or also the degree of the system sigma. And we say that sigma consists of, or is a system of n elements, or the number n shows how many elements are contained in sigma. So we're thinking about n here as kind of a cardinal number. Okay, so in answer to the question, how many? As opposed to ordinal numbers, which would, you know, we'd be thinking more in terms of order. You know, which position in the number series does this occupy, so to speak. So we're talking about how many here, how big, in terms of how many. If numbers are used to express accurately this determinate property of finite systems, they're called cardinal numbers. As soon as a determinate similar transformation psi of the system Zn is chosen, by reason of which psi Zn is equal to, and it's not Z, it's sigma. I remember seeing this. It should be a sigma. Then to every number m contained in Zn, i.e. every number m which is less than or equal to n, there corresponds a determinate element psi m of the system sigma, and conversely by 26 to every element of sigma, by the inverse transformation psi bar, there corresponds a determinate number m in Zn. So we've got the numbers 1, 1 primed, m, n. So we can transform these into, so we've got on the one hand Zn, and on the other hand we've got sigma. So we can apply the transformation sigma psi to go from Zn to sigma. So in general we'll have psi m and so on. But then we've got, because psi is a similar transformation, then it has an inverse, which is also a similar transformation. We can go the other direction as well, using psi bar. To take us back into Zn. Very often we denote all elements of sigma by a single letter, example alpha, to which we append the distinguishing numbers m as indices, so that psi m is denoted by alpha m. So this seems quite an innocuous statement, but it's quite useful, I guess. What we're saying here is that we can describe the elements of the system sigma as follows, as the elements alpha 1, alpha 2, alpha 3, up to alpha n. Okay. Rather than writing psi 1 prime, I'm sure that if you're familiar with sequences of numbers and things like that in contemporary mathematics, you'll have seen this kind of notation. So he's kind of justifying this notation, that we've got this one-to-one correspondence. And this kind of idea is still used. You know, you read books on modern set theory. This notation will be derived, it will be explained away in a very similar sort of way. We say also that these elements are counted and set in order by psi in determinate manner, and call alpha m the mth element of sigma. If m is less than n, then alpha m primed is called the element following alpha m, and alpha n is called the last element. So the last element will exist because we know that sigma is finite, because Zn is finite, and it's similar to, well, this part of sigma at least. Then this part of sigma must also be finite, and therefore there must be a last element. In this counting of the elements, therefore, the number m appears again as ordinal numbers. Okay, so in the sense, so in counting 1, 2, 3, so on and so forth, we understand this as kind of setting this setting in order, right? First, second, third, and so on. So we're seeing a relationship here between numbers being used as cardinal numbers in order to describe how many or how big is this system, but also we're using the same symbols effectively to count, to set in order, to put it in a particular order, hence ordinal numbers. So in the finite case, we have this very close relationship between cardinal numbers and ordinal numbers, a relationship which doesn't exist when it comes to infinite systems. Okay. Or it doesn't necessarily exist. Theorem 162. How are we doing for... Oh, right. All systems similar to a finite system possess the same... where was I? All systems similar to a finite system possess the same number of elements. So the proof follows immediately from 33 and 161. So all systems similar to a finite system, what is 160? Right, possess the same number of elements. So they must so 33. Just let me read it again. Finite similar systems, then. Yeah, so there's right, okay, yeah. So if we've got a particular system A, and then we've got two other systems B and C which are similar to A, by 33 they must be similar to each other. B and C must be similar to each other. So if A has the number n, then B and C must also have the number n. So the proof, yeah. Theorem 163, the number of numbers contained in Zn, i.e. of those numbers which are less than or equal to n, is n. So this is because Zn is similar to itself. Theorem 164, if a system consists of a single element, then is the number of its elements equal to 1, and conversely. So the proof follows immediately from 2, 26, 32, 102. So we've seen that so let's go on to the next page. Z1 is just equal to 1. So any system... what's 26? Oh, yeah, similarity. 32... I don't know what 32 is. Systems R and S are said to be similar when there exists such a similar transformation. So that's a definition. 102. Z1 equals 1 and 161. So, yeah. Z1 has number 1. Basically by definition, I guess. So any system that is similar to Z1 will have the same number of elements. It's kind of obvious. Nothing really for me to say. I was expecting there to be more for me to say about that, but a bit of an anticlimax, I guess. Okay, so theorem 165. If T is a proper part of a finite system sigma, then is the number of the elements T less than that of the elements of sigma. I think I might make this the last theorem that I go through for the time being. I think I'm going to have to do another video. So by 68, T is a proper part of a finite system. So T is finite. So sigma is finite. So any part of a finite system is also finite. So T is a part of sigma. So T is finite. So therefore T is similar to Zm, where M denotes the number of the elements of T. If further n is the number of elements of sigma, sigma is similar to Zn, then by 35, T is similar to a proper part E of Zn. T is similar to a proper part of Zn. So let me just, by 35, just let me double check what that says. 35. If R and S are similar systems, then is every part of S also similar to a part of R? Every proper part of S, because T is a proper part of sigma, is also similar to a proper part of R. So, right, yeah, okay, I'm happy with that. So because sigma is similar to Zn, T is a proper part of sigma, so T must be similar to a proper part E of Zn. And by 33, also Zm and E are similar, because T is similar to Zm, T is similar to E, so Zm similar to E. If then we were to have n less than or equal to m, hence Zn, so that's equivalent to Zn is a part of Zm. I can't remember. It's 101 apparently. I've written a little note there. Just let me double check. By 101, n less than or equal to, maybe not, or maybe 100, sorry. Yeah, 100. Theorem 100. Zn is a part of Zm. Then by 7, E would also be a proper part of Zm. So Zn is a part of Zm, and Zm is similar to E. E is a proper part of... Oh, sorry, no, I'm looking at it the wrong way around. E is a proper part of Zn. E is a proper part of Zn, and Zn is a part of Zm. Not necessarily a proper part, but nevertheless, E will be a proper part of Zm by virtue of the fact that E is a proper part of Zn. So this is using theorem 7. And consequently, Zm, an infinite system, because remember that Zm is similar to E, but E is a proper part of Zm. So Zm would be similar to a proper part of itself, which can only happen, which is the definition of an infinite system. So Zm would satisfy the definition of being an infinite system, which it's not. We know by 119 that Zm is a finite system, so we've got a contradiction. So we can't have n is less than or equal to m. We must have m is less than n. So does that prove what we needed to prove? If T is a proper part of a finite system sigma, then is the number of the elements of T, which was m, less than that of the elements of sigma, which was n. Yeah, we've got m is less than n, and we're done. Okay, so I'm going to leave it there for this video. As I suspected, I'm going to have to split it into two videos. There's not really much left to go through with this chapter, but I will be sure to finish things off over the coming of the next few days or so. So any questions that you have, please feel free to ask. Thank you for watching if you've made it to the end of the video, and I will look forward to seeing you in the next video.